Okay, so the Otis lesson looks like this. We've got, again, there's the last things are some instructions for linear regression for each calculator. And then we're going to start with the notes, these Beer's Law notes here. And then there's 3 sets of practice problems. And what we'll do is we'll work through as many of those as you guys need to feel comfortable with doing it. And so let's see. All right, let's go. Okay, so we'll start with the notes, okay, which look like this here. Okay. All right, so you did a little bit of work with that simulation thing, and essentially what Beer's Law does is it looks at, okay, so say this is our solution, like we have a little container, they call it a cuvette, and we put it in the machine, and so our solution, right, this represents that cuvette that has the solution in it. And so what the spectrometer does is that it knows the intensity of the light going in. So this is that right there, that is intensity of the light source. Okay, and then it measures, this is the intensity after passing through the solution. Okay, and so what Beer's Law says is that the absorbance, right, and that A with the little symbol and the lambda, so lambda is the wavelength of the light. All right, and in the simulation, you saw where you could like use different wavelengths of light, and depending on which solution you had, um, some wavelengths work better than others. And so essentially, when we, in the spring, we're going to actually work with spectrometers. And one of the first things you do with the solution is you run a scan through all the different wavelengths of light, and it'll spit out a graph that has your absorbance versus your wavelength. And it will, like, and so it'll look kind of like sort of this, right? And so whatever this wavelength is here with the maximum absorbance, that's the one that you would choose to actually use for your data in there, okay? And so that's what that A at a particular wavelength means. And then this right there is what they call the absorptivity. And this is all in the writing. I'm just trying to kind of pull the key things out of these notes for you. And the key thing about that is that it is specific to the solution. So each solution is going to have this characteristic which looks at how much light does it absorb at that particular wavelength. And then C is our concentration. Put in a different, or I'll put it over here. C is our concentration. And then I is the path length, which is essentially this, it's the width of our cuvette. Okay, And so usually that particular thing will stay the same. Okay, so what we're going to look at, this method that we're using is very standard, not just with solutions, but essentially let's go down to our graph here. Okay. So there. All right. So essentially what the way that you work this is that you take and measure the absorbance of several data points, okay, where you know the concentration. All right. So I might have, and Vic, this has got like several points here. All right. So I take that solution where I know what the concentration is and I generate this line of absorbance versus concentration, okay, with my known solutions. And then I can use that line. If I have an unknown solution and I measure the absorbance, then I can use that plot to figure out what is the concentration of the unknown. And this is a pretty standard method that you use with experimental data, where you know that there is a linear relationship. And so you generate your line with some knowns, and then that way you have something you can use to find unknowns with. All right, and so we're going to start out, let's just use this data here. So concentration versus absorbance. All right, and let me pull up mine. Okay, so this is my HP prime here. So we have absorbance is our Y and concentration is going to be our X on there. So if we plot it, let's see, I got to go. All right, so on the HP prime, I would put in my data. Let me see if I can make that a little bigger. So now on the HP prime, once you get your data put in, all right, then again, depending on what calculator you use, you want to do your plot on there. And so in the HP prime, it has the symbolic view where you can tell it what you want your X and your Y to be. And I think that's what I did there. Yeah, okay. And then I tell it to plot. And so then I get this best fit line here. And then it's going to give me my equation there. And so I can use that equation then to solve for the absorbance of a particular unknown. So we'll pick one. So say, and I'm going to just write so Y equals, oops, get it back up there. Say 137.3x, 137.3x. Okay, and then calculator. Minus 0.008, I think it said. 0.0084. Okay. All right. And so that's my equation that I can use to solve for if I find an experimental absorbance, which is my Y, then I can solve for the X. And on here, and most Beer's law plots, because your y-intercept is typically it's 0, or with experimental data, it should be really, really close to 0. So that's why on this worksheet here, right? They just dropped out the y-intercept off of there because it's so much smaller than the what you're going to get from your 137.3 plus x or 137.3x. So, is there anybody here that is using the all right, let me put I'm going to put my data into the TI then, and let's just see. Wait, clear. Second list. Okay. Okay, stats, edit. All right, so L1, 0.0012, 0.0024, 0.0048, 0096, 0.0019, and then L2, oh, I forgot my 0. Shoot, go back. Let's try putting the 0 in. On 6.0019. All right, and then if I go back up, 0.15, 0.31, 0.7, 1.25, and 2.62. Okay, so now go back to stats, calc, linear regression, and I'm doing L1, comma L2. Hit enter. Okay. Oh, and that gives me a different value. Huh. Let me go back and check my.
All right, I think I got mine sort of to work.
Okay. Are you getting the same equation?
Let me look.
When I did it, I got y equals 137.61 x minus 0.0123.
Okay. Okay. So that's close to
Where do
what
you
they
see
got.
y? How do you find y? How do you find y?
In the linear regression, that equation they give you, it's always y equals that.
So I have to like do the math myself, or?
For, you mean like if you have an unknown?
Oh, what are we putting in? Oh, okay.
So right now we're just getting the line, but for some reason mine is not. Huh, when I put it in, what am I doing wrong? X plus B. And I did list 1, comma, list 2. Okay, I don't know why my TI is not working well for me. Okay. And then, all right, so let me do in the TI. All right, stats. All right. Okay, so say, all right, we'll just make sure we're doing this right. So say I have,
I didn't get the same R2. Is that what we're trying to find?
No, this, you want the equation is what we're trying to find.
Is that somewhere on the notes?
No, it's when you do your the calc, go down to linear regression, and then you put in your x, like the list that your x is in, comma, the list that your y is in. Then if you hit enter, it should come up with your A, like it should come up with the
It
The
gave me
A and the B.
B R squared and R.
Okay, so it didn't give, did it give a B?
Yes.
Okay, yeah, so that's your, so it's giving you the, in the form of y equals ax plus b.
Okay.
So you'll just plug in those numbers there, and that's your equation that you'll be working with. All right, so let's look at, so say, and you can do this with your calculator, or you can just do it by plugging in numbers. Say I get an absorbance of, say my unknown gives me an absorbance of say 0.85. Okay, so what we want to do is we want to find out, okay, what is the concentration of that? So again, we can use our, plug it into our 0.85 equals 137.3 times 0.85. And if you want to be very precise, you can include that the y-intercept, but it's probably not going to make much difference at all. So oops, 0.3 times 0.85. Oh, wait, what am I doing? Let's try it. We're solving for x. Good grief. I need some more coffee, I think. Okay, here we go. Clear. So 0.85 plus 0.084, and then divide by 137.3. That doesn't make any sense. Yeah, that's, Are you getting like 0.0063?
Give me a second. I
Okay. Oh, okay.
plugged the 0.85 in the wrong place.
Because I'm getting a number. It doesn't make any sense when I do that, because it's not, it should be. Oh, no, that's right. 0.00. Okay, that is, I'm looking at the wrong column. I'm getting 0.00, we'll just round it, 63.
Yes, that's about
Yeah,
what I got.
which I was thinking it should be in between these two, because my absorbance I chose was in between those two. Okay, so that makes sense. Okay. All right, so let's, and again, this just has the procedure that we just followed that's in those notes. All right, so let's go to the, wait, wrong one. Okay, this one here that says activity number 3 in the lesson that says beer practice. So let's take a look at that one, which should look, I think it's this one here. Okay, now sometimes instead of absorbance, they give you transmittance. All right, and so when that, if you get that, then this is the equation that we use to get from transmittance to absorbance. So if we take, so for example, we've got, let's see, so negative, I need to put my other glasses on. All right, so negative, well, transmittance 100. So negative log of 1. Okay, so that's going to be, so absorbance, if I make a separate table, absorbance, so that's, first one's going to be 0. Then if I do the negative log of 0.966, I'm getting 0.015, and the negative log of 0.902. So I'm getting 0.045, and the negative log of 0.839. I'm getting 0.076, the negative log of 0.78, getting 0.107, or 108 rather. And then the negative log of 0.724. All right. So if we have absorbance, we've got the, or if they give us transmittance, then we have that extra step of putting that into there. Okay, so let's do our plot with this one. All right. Okay, so stats, edit, and list 1, 0. And this is one thing to remember in doing these. Well, no, that just applies to the HP prime that's in there. Okay, let's go. 0.01, 0.030, 0.05, 0.07, 0.09, 0, 5, okay, and then we'll do calc. And so see if my calculator will give me the right answer this time. All right. So my equation, I'm getting y equals 1, I'm going to round it, 1.56 x minus 7 point, now let me write that somewhere else. Write it down here. Y equals 1.56 x minus 7.95 times 10 to the negative 4th. Is that what you guys got?
That's what I got.
Oh, okay, good. I was worried that my calculator was being weird after that last one. Okay, all right, so then in the question it says we want the concentration of an unknown manganese to chloride solution that transmits 85%. So if my percent T is 85%, then my absorbance, we're going to do negative log of 0.85. So I'm getting an absorbance of 0.071. And so then if I plug that in, oh, this is not giving me very much room here. Let's see. And it, one, and then plus 7.95.
How'd you get that absorbance value for the?
I did the used A equals the negative log of 85 divided by
I did
100.
0.85. Sorry.
Let's see. Okay, so that E4. Okay, and divide by 1.56. So I'm getting X is 0.046. And let's see, does that make sense? So 85 would fall in here. Yes, okay. So that does make sense. It's in between what we would want. Okay so far?
I didn't get the same thing.
Okay, did you get the same?
I got
When
the
you d-
same X and, or yeah, I got that.
Okay,
So do you
all
plug
right.
it? Where are you
Yeah,
putting the 0.071?
that's the absorbance, so it's the Y.
The Y. So that's
Uh-huh.
what you're trying to get.
No,
So you're solving
trying.
for X.
Yes, you're solving for X.
Okay.
Uh-huh. Mm-hmm. Come over a bit. All right. So here in this one, we're going to, all right, here they're given the concentrations in parts per trillion, which we still do the same procedure. So if I have concentration, and then they're giving us percent transmission again. So it says a 2 parts per trillion is 85.
I got it that time.
So, oh, great, great. And then a 6 is 63, and a 10 is 46.3. So we're going to find our absorbance. So negative log of 7. I'm getting 0.067. The negative log 0.63. So I'm getting 0.20. Oh, wait. Yeah, 0.463. 0.3. Hang on, I did something wrong. Let's do that again. Negative log 0.63 is 0.2. And the negative log of 0.463. 0.3. Okay. All right. So then, all right. So now we're going to plot, do our stat plot. Down. All right. So to stat edit. All right, L1 is going to be 2, 6, 10. And this is 0.067, 0.2, 0.33. Delete, delete, delete. Okay, set calc. One, comma, 2. All right, so I'm getting, this is number 2. I'm getting y equals 0.0329x plus 0.00175. Okay, so then now it's saying once this one, solution transmits 50%, what is the, so if my percent transmission is 50, that means my absorbance would be 5.301, right? So then if I plug that in, I get y. No, that is my y. Sorry, stop. Let's do that again. I get 0.301 equals 0.0329x plus 0.00175. So x then is going to be 301 minus 0.00175 divided by 0.0329. So I'm getting 9.1, which that is a reasonable answer there.
Hi, Mr. Dilly.
Mm-hmm.
I'm a little bit confused on the concentration.
Mm-hmm.
I thought it was in moles, or not moles, but molarity. And I don't, because we went from parts per thousand to, how does that, does it just convert from, you get what I'm saying there?
Well, for this, to do these plots, you can use any measure of concentration. It doesn't have to be molarity. It typically is, especially on the AP exam, it'll be molarity. But if it's like here, parts per trillion or parts per billion, as long as all the concentrations are in the same unit, then this method works with it.
Okay, thank you.
Mm-hmm. Okay. All right, and then now this what they call the bonus question, here you're kind of going the other way, where it says you want the percent transmission from, and it's giving you a concentration on that. So if we, all right, let me pull this up on mine so I can, I just need to get to another sheet of paper because on this thing it's getting too crowded. But I want to, let me pull up so I can see that worksheet. All right. Okay, so, all right, so if I have, I'm going to go over here. All right, and we'll just do one. Say if I have, if my concentration is 4 parts per trillion and it wants to know what the percent transmission is, okay? So we're using the same equation. So y equals 0.0329x x plus 0.00175. And it's just that this time concentration it's our x. So here we have y equals 0.0329 times 4 plus 0.00175. So that gives me a y of, or 0.0329 times 4 plus 0.00175. So I get y equals 0.133, which that is our absorbance. And so now we want to go absorbance back to transmission. And so if you look over here, all right, we're essentially doing the inverse log, the negative inverse log of that. So my percent transmission is going to be, so my percent transmission then is going to be 10 to the negative 0.133 times 100. So I do inverse log to negative 0.133 times 100. And so I'm getting 73.6. That would be the percent transmission. All right. So far, so good?
I got that too.
Okay, good deal.
Okay.
All right, so now let's go down to our next one. Move this over. Okay. So here, all right, so here we've got our data. I'm going to get my absorbance with that. So that's going to be 0, but so 0.945, 0.245, I go log 0.894, 0.0487, 0.846, 0.0726, and negative log 0.796. It's 0.099. Okay, so now going to stats and L1, we've got 0, 0.252, 0.501, 749, 2, and then got 0, 0.0245, 0.0487, 0.0726, 0.099. Okay, stat calc. Whoops. Okay, so I'm getting y equals 0.097x plus 3.05 times 10 to the negative 5th. Okay, and then part C says if it's 96%, it wants to know what is the concentration. So negative log 0.96. So my absorbance is 0.0177. All right, and then I plug that in. So see that minus 5 divide by 0.097. So I'm getting that x equals 0.182 for the concentration, which is about, yeah, because we would expect it to fall like in here. So that makes sense. Are we all good on that? Oh, go ahead.
So if it falls in that range, because we use the mass rather than like the molarity, you have to you would have to convert that to molarity, right? If it asks for the concentration.
Yes. So this is going to be, let's see, did it tell us how much? Yeah, in 100 milliliters. So, all right, so let's go ahead and do that. So it's copper sulfate 5H2O. So this is grams of CuSO4.5H2O. All right, so we calculated this so much you'd think I'd have this one memorized. Where'd my periodic table go? Here we go. All right, so 5 plus 4. So on this I get 159.53 plus 5 waters. So that gives me 249.63 is my grams per mole for that. Okay, so 0.182 divided by that. So I'm getting, that is 7.29 times 10 to the minus 4th moles. So my molarity is going to be 0.29 times 10 to the negative 4th moles. And it said it was a 100 milliliter flask, so 0.1 liters. So I get a molarity of 0.00729. Okay. Okay, let's look at, I want to just glance at the other two. All right, so this is just giving us the data, and then it's asking us for a particular unknown. Same thing there. I'm just making sure the other two sets of problems that there isn't anything we haven't looked at. Okay, give us a curve, wants to know that, gives us the data, percent transmission. Okay. Yeah, they're all pretty straightforward. So there are 5 in the third set, and I think 2. So seven problems for you guys to go ahead and do your linear regressions on it. And then tomorrow we'll start out, we'll check your answers to those 7 and see if you have any other questions, unless there's more questions now. Is everybody good on this?
I'm good.
Okay. Everybody else okay?
I'm good.
Okay, good deal. So we will check answers tomorrow, and then tomorrow we're gonna work some practice free response and do some review in there. And let me see, what else did I have? Yeah, we'll do that, and then I don't know. I had down here to do the test on Wednesday, but we'll play it by ear. We'll see how you guys feel tomorrow. After we do, I'll pick free responses. So essentially, we're going to do a review with free response questions tomorrow. But I'd like to test Wednesday if we can, but we can kind of decide if we feel like we aren't ready or not. Okay. All right. So if there aren't any more questions, or if something comes up and you have a question, just shoot me an email. Okay. And I will see you guys tomorrow.
Hey, Mr. Billy.
You too. Have a good day.
Thank you.